Okay, so here we've got the notes for section 3.3, which deals with logarithmic functions and their graphs. So we've got here the inverses of exponential functions. So it says if a function passes the horizontal line test, then the inverse of the function is also a function. So remember, the vertical line test is used to determine if something is a function. The horizontal line test tells you that if you take the inverse of your original function, is that thing also a function? So for example, if I take this, which is f of x is equal to x squared, this graph is a function because vertical lines only cross once. However, it is the inverse, so f, this guy, not a function because it fails, the original function fails the horizontal line test. And the inverse would actually be, if you graph f, the inverse function, it actually looks like this, which is definitely not a function because it fails the vertical line test. So an exponential function f of x equals b of x would pass the horizontal line test, so it has an inverse function that is also a function. This inverse is the logarithmic function with base b, denoted log base b of x, or more simply log bx. That is, if f of x equals b of x with b more than 0 and b not 1, then the inverse function is log base b of x. And then here's your kind of definitions. So y equals a log base b of x is true and only if b is to the y-th is equal to x. So a logarithm returns the exponent used on the base to get that value. So like here, log base 2 of 8 is what power of 2 is equal to 8, is what the question's stating. So we need to get a common base here. So we need to write 8 as some power of 2. So 2 to the x. So 8 is actually 2 cubed. Since the bases are the same, the exponents have to be the same. So that means that x has to equal 3. And we just keep repeating that process. So this is saying 3, the base, to what power is the square root of 3. So this would become 3 to the x is equal to 3 to the half, which means that x is equal to 1/2. So here this would be 5 to the x is equal to 1/25. So this one's a bit tricky because two things are happening. So the first thing I'm going to do is I'm going to bring that 25 out of the bottom of the fraction by giving it a negative exponent. Now I'm going to have to write 25 as a power of 5. So 25 is 5 squared. So then this would become, when you raise a power to a power, they multiply. So this, which means that x is equal to -2. So log base 4 of 1, so this would be 4 to the x is equal to 1. This is a definition because anything raised to the 0th power is 1. So x has to be 0. And here, this is 7 to the x is equal to 7. So even though it's not shown, this technically has a 1 exponent, which means that x is equal to 1. So these are two actually kind of definitions. The log of any base of 1 is always 0, because 0 is the only exponent that returns 1. The log, if the base and the value are the same, it's equal to 1. 7 to the first is 7. 4 to the 0th is 1. 5 to the -2 is 1/25. 3 to the half is the square root of 3. 2 cubed is 8. So the exponential returns the the logarithm returns the exponent. Okay, some definitions we just talked about. Log base b of 1 is always 0, regardless of what the base is. Log base b of b is equal to 1, because b to the first is b. Log base b of b to the y is equal to y, because b to the y is b to the y. So like if you rewrote this one, that'd be like asking log base 4 of 4 squared. Well, that would become 4 to what power is 4 squared, so it's just 2. B to the log b is actually just x because, how to phrase this? First of all, they're inverse operations, so they cancel each other out, but log base b of x is equal to log base b of x. So this is actually working in reverse. So I don't know why we just did these numbers, because you already know these. These are 3. Or did I do more work than I was supposed to do? No? Example 1, this is evaluate. So this one was 1/2. And this log base b is just 11. That's using this rule. B to the log b of x, so base to the log base of x is just the x value. Okay, so there are two general types of logarithms that get used a lot. The first is the common logarithm. That's logarithm base 10. That's the button on your calculator that just says log. With base 10 of the common logarithm, because we count in base 10, so that's why the common log. So the subscript of 10 is usually dropped when you use a common logarithm. So if you don't see a base, it means it is base 10. If you see a base, you have to use that one. So specific rules just for common logs, they are the same as the basic properties of logs, just with base 10 instead of log base b. Okay, so evaluate the following. So the log of 100, so base is assumed to be 10, so 10 to the x is equal to 100. So I would need to write 100 as a power of 10, which means that x is equal to 2. Now this can also be done on your calculator because your calculator has a log button. Here, this would be 10 to the x. Now the fifth root is the same thing, as a 1/5 power. So in this case, x is equal to 1/5, or if you want the decimal, your calculator will probably tell you 0.2. A log of 1/1000th, so 10 to the x is equal to 1 over 1,000. So 10 to the x is equal to 1,000 to the negative 1. 1,000 written in terms of tens is 10 cubed. So this is the same thing as 10 to the negative 3, so x is negative 3. This one, so 10, log base 10, this is just 6. And your calculator will handle all of these. I can just type these all into my calculator. So log 10 is 1. So the first one was log 100 is 2. Then I had log of the fifth root. Let's find my fifth root of 10 is, there's your 1/5, the 0.2. Whoops. The log of 1/1000th, negative 3. And 10 to the, log of 6. Your calculator has all those buttons. Okay, so use a calculator to evaluate the logarithm expression was defined. Okay, well, so these are all pure calculator problems down here. So log of 34.5, this is about 1.54. The log of 0.43 is about negative 0.37. And then I'm not going to do the check, but if you do 10 to the 1.54, you'll get about 34.5. If you do 10 to the negative 0.37, you'll get about 4.3. The last one, log of negative 3, is math error. This is actually undefined because you can't take logarithms of negative numbers. Because if you think about what this question is asking, it's saying 10 to what power is negative 3? Well, that can't happen. Raising a number to a power can't change its sign. So there's no way this problem can work. If you want to do the check, 10 to the 1.54, I guess we'll do the check. This comes out to be about 34.67. So it's close. It's not exact because that's a rounded value. The same thing's going to happen down here. We're going to have to do some rounding. So this comes out to be actually 0.427, which would round to 0.43. Okay, so down here it says solve each equation by changing it to exponential form. So now we're given our exponent. So log x is equal to 3 means 10 cubed is equal to x. So 10 cubed is 1,000, so x is 1,000. Here, that's my exponent, so this is 5 squared is equal to x. Base exponent is equal to that, so not 5 squared, 2 to the 5th. 2 to the 5th is 32, so x is 32. Okay, so the other type of logarithm that gets used a lot is the natural logarithm, base e. Because these appear in nature a lot, that's why they're the natural logarithm, e and this. So ln is the symbol used. It's the same thing as log base e. So your calculator does have a button, usually it's either right next to the regular common log button. Properties are all still the same as they were before because it's still just logarithm. Ln of 1 is 0 because e to the 0, so e to the first is e, so 1, so on and so forth, all the properties rule. So evaluate the following, the natural log of the square root of e. So this is saying e to what power is e to the 1/2? Well, x has to be 1/2. 1 to the 1/2 is 1 1/2. 1 to the 1 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 is Here, this is saying e to what power is e to the fifth? Well, 5. And then this e to the ln of x is just always equal to x, so this is just equal to 4. And your calculator will handle all of these because your calculator has a natural log button. So these ones down here, once again, are calculator problems. The natural log of 23.5 is about 3.16. And if I do e to the 3.16, that comes out to be about 23.57, so pretty close. This one would come out to be about 0.48, which is negative 0.73. And this one, once again, negative number, so no solution. You cannot take the logarithm of a negative number. There is no way to make e change sign by using a power. Same thing for 10. All right, so here we've got the graphs. So here's e to the x and ln x, so they're inverses because they're reflected across the line y equals x. Here's 10 to the x and log base x, or common log, so inverses again. So here it says describe how to transform the graph. Okay, so same rules as before. So typically you have, if you want the generic version, a log or ln of, we'll put a b here, x minus h plus k. So a controls vertical stretch or x-axis reflection if it's negative. B is horizontal compression or y-axis reflection if it's negative. H moves the graph left or right, the opposite of what it appears, just like always, and K moves the graph up or down. So this one I have a +2, so I have an H value, so it looks like it should go right 2, so this one goes left 2. This one I actually need to rewrite. This is the same thing as negative x plus 3, because I need my x first. So my b value is negative, so this is going to be a y-axis reflection, and it's going to go left 3, because of that +3. 3 log x, so this is a vertical stretch by 3. And this one is written not how I usually write it. I usually put the +1 at the end, so this one is just up 1 unit, because that's a k value. And that brings us to the end of the section.